Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We shall also learn how to calculate percentage voltage regulation and efficiency of transmission of this line using those constants. Neglecting Likens and using nominal pi method, we have to determine the voltage regulation and the efficiency of transmission of a three-phase 50 Hz 80 km long transmission line delivering 24 megavolt ampere at 66 kilovolts and 0.8 power factor lagging to a balanced load. The conductors are made of copper, each having resistance of 0.12 ohm per kilometer, 1.5 centimeter outside diameter, spaced equilaterally 2.5 meter between centers. Let us first write down the given data. Load SL equals to 24 megavolt ampere, that is equal to 24 into 10 to the power 6 volt ampere. Line to line receiving end voltage VR line equals to 66 kilovolts, that is equal to 66,000 volts. For star connected system receiving end voltage per phase, VR equals to VR line divided by root 3, that is equal to 66,000 divided by root 3, that gives us 38,105 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 24 into 10 to the power 6 divided by root 3 into 66,000. That gives us 210 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 210 ampere at an angle minus 36.8699 degree. Here, load current IL equals to receiving end current IR. Power delivered to the load PL equals to SL into cos phi L. Using values we get 24 into 0.8, that is equal to 19.2 megawatt. Given length of the transmission line D equals to 80 kilometers. Diameter of the conductor D1 equals to 1.5 centimeter. Equilateral spacing between conductors D2 equals to 2.5 meter, that is equal to 250 centimeters. Let us now calculate radius of the conductor. R equals to D1 by 2, that is equal to 1.5 divided by 2, that gives us 0.75 centimeter. Expression for inductance per kilometer per phase L1 equals to 0.05 plus 0.2 into log of D2 upon R millihenry. Using values we get 0.05 plus 0.2 into log of 250 upon 0.75 millihenry, that gives us 1.212 millihenry. Now we shall calculate inductance per phase L equals to L1 into D. Using values we get 1.212 into 80, that is equal to 96.96 millihenry or 0.09696 Henry. Expression for capacitance per kilometer per phase C1 equals to 1 upon 18 into log of D2 upon R microfarad. Using values we get 1 upon 18 into log of 250 upon 0.75 microfarad. That gives us 0.0095635 microfarad. Now we shall calculate capacitance per phase. C equals to C1 into D. Using values we get 0.0095635 into 80, that gives us 0.765 microfarad or 0.765 into 10 to the power minus 6 farad. Given resistance per kilometer per phase R1 equals to 0.12 ohm. Let us now calculate resistance per phase R equals to R1 into D. Using values we get 0.12 into 80, that is equal to 9.6 ohm. We have computed inductance per phase L equals to 0.09696 Henry and capacitance per phase C equals to 0.765 into 10 to the power minus 6 farad. Now we shall calculate inductive reactance per phase XL equals to 2 pi F into L. Given supply frequency F equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.09696. That gives us 30.461 ohm. And capacitive susceptance per phase BC equals to 2 pi F into C. Using values we get 2 pi into 50 into 0.765 into 10 to the power minus 6. That gives us 240.332 into 10 to the power minus 6 mho. Now we shall determine series impedance per phase of the transmission line. Z equals to R plus JXL, that is equal to 9.6 plus J times 30.461 ohm. This may be written in polar form as 31.938 ohm at an angle 72.5074 degree, and shunt admittance per phase Y equals to J times BC, that is equal to 0 plus J times 240.332 into 10 to the power minus 6 mho or 240.332 into 10 to the power minus 6 mho at an angle 90 degree. We have obtained series impedance per phase of the transmission line Z equals to 31.938 ohm at an angle 72.5074 degree, and shunt admittance per phase Y equals to 240.332 into 10 to the power minus 6 mho at an angle 90 degree. Let us now calculate Y into Z. Using values we get 240.332 into 10 to the power minus 6 at an angle 90 degree into 31.938 at an angle 72.5074 degree. That gives us 7,675.7234 into 10 to the power minus 6 at an angle 162.5074 degree. This may be written in Cartesian form as minus 0.0073208 plus J times 0.002307 Now we shall calculate 1 plus 1/4 of y into z, that is equal to 0.99817 plus j times 0.0005768. This may be written in polar form as 0.9981702 at an angle 0.0331 degree. For pi equivalent circuit, A equals to D equals to 1 plus half of y into z, that is equal to 0.99634 plus j times 0.0011536. This may be written in polar form as 0.996347 at an angle 0.0663 degree. B equals to Z, that is equal to 31.938 ohm at an angle 72.5074 degree, and C equals to Y into 1 plus 1/4 of Y into Z. Using values we get 240.332 into 10 to the power minus 6 at an angle 90 degree into 0.9981702 at an angle 0.0331 degree. That gives us 239.892 into 10 to the power minus 6 more at an angle 90.0331 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 38,105 volts at an angle 0 degree. We have computed receiving end current IR equals to 210 ampere at an angle minus 36.8699 degree. We have determined for pi equivalent circuit generalized constants A equals to D, that is equal to 0.9963407 at an angle 0.0663 degree. B equals to 31.938 ohm at an angle 72.5074 degree, and C equals to 239.892 into 10 to the power minus 6 mho at an angle 90.0331 degree. Expression for sending end voltage per phase, Vs equals to A times VR plus B times IR. Using values we get 0.996347 at an angle 0.0663 degree into 38,105 at an angle 0 degree plus 31.938 at an angle 72.5074 degree into 210 at an angle minus 36.8699 degree. That gives us 43,416.431 plus j times 3,951.7876 volt. This may be written in polar form as 43,595.907 volt at an angle 5.2 degree. And expression for sending end current per phase, Is equals to C times VR plus D times IR. Using values we get 239.892 into 10 to the power minus 6 at an angle 90.0331 degree into 38,105 at an angle 0 degree plus 0.996347 at an angle 0.0663 degree into 210 at an angle minus 36.8699 degree. That gives us 167.52511 minus j times 116.204 ampere. This may be written in polar form as 203.8824 ampere at an angle minus 34.747 degree. or no load receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 43,595.907 at an angle 5.2 degree divided by 0.9963407 at an angle 0.0663 degree. That gives us 43,756 volts at an angle 5.1337 degree. Let us now calculate voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 43,756 minus 38,105 divided by 38,105. That gives us 0.1483 per unit or 14.83%. We have computed sending end voltage per phase Vs equals to Vs at an angle delta equals to 43,595.907 volt at an angle 5.2 degree, and sending end current per phase Is equals to Is at an angle minus phi 1 equals to 203.8824 ampere at an angle minus 34.747 degree. For star connected system, sending end current per phase equals to sending end line current, and line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 43,595.907, which is approximately equal to 75.51 into 10 to the power 3 volts or 75.51 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 5.2 degree plus 34.747 degree. That gives us 39.947 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 39.947 degree. That gives us 0.76664 lagging. Now we shall calculate sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 43,595.907 into 203.8824 into 0.76664, which is approximately equal to 20.4427 into 10 to the power 6 watts or 20.4427 megawatt. Now we shall calculate efficiency of transmission. Eta T equals to PL divided by PS. We have computed power delivered to the load PL equals to 19.2 megawatt. Therefore, eta T equals to 19.2 divided by 20.4427. That gives us 0.93921 per unit or 93.921%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We have also learned how to compute percentage voltage regulation and efficiency of transmission of this line using those constants. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.